Okay, so hi everyone. So let's start. One of the things before we get into curvature, one of the things I wanted to make sure that we discuss is this idea of integral of. Or maybe I should say integrals because there are like two types of integrals that we're going to talk about. Integrals of vector valued functions. So the idea here is like this. So we have this vector valued function again, R of t, which is like, let's write it as f of t, g of t, h of t. We can also write it really in vector form, say f of ti plus g of t j plus h of t k. And you can specify the domain of t if you want, but it depends on the context, right? So say t is between b and a. So this is a vector, has three components like that. So we define the derivative of the vector valued function, velocity, and we have different interpretations, right? So, so you can guess that it just makes sense to also try to define integrals, right? Because we are doing calculus of vector valued functions, right? So we should do derivative and integration. So the integral of such things. So first of all, there is this idea of indefinite integral, right? Okay, so here is definition. So what you can do, you can just take indefinite integral of each component, right? So then the result is going to be a vector again, because each component gives you a function, a new function. So it's a vector valued function, right? So this is going to be equal to integral f of t dt times I. Remember, this I is a unit vector, so this is separate from this. So you have to do this in indefinite integral plus integral g of t dt j plus integral h of t dt k. Right? So it has three components. So it's a vector. It, again, is a vector valued function. Just define it. So this is the definition. I mean, you may like it, you may not like it. The point is, if it is useful or not, what you can do with it, stuff like that. Right? And we have also definite integral. So this is completely parallel to the story with calculus. Right? We also have definite integral. Okay, so now the definite integral, we have integral a to b, for example, f of r of t dt. Again, we just do definite integral component by component, right? So this is like integral a to b of t dt I plus integral a to b g of t dt j. So let me put it a little bit separate, maybe. But these are really separate. Plus integral a to b h of t dt k. Now, this is a vector also, right? So this is a vector. However, of course, it's a vector, but the components are just numbers, right? But this one, the indefinite integral, is a vector valued function. So this is a vector valued function, but this is really just a vector because the components are just specific numbers, right? So it's a vector. But this one is a vector valued function. So So let me give you a simple example. I mean, this is very straightforward. So example, let R of t equal to ln t I plus e to the negative 3t j plus tangent of t maybe. Okay, let's take t between, for example, 1 and 2. It doesn't matter. So the question is compute integral, indefinite integral RT dt, right? Definite integral RT dt, and definite integral, well, 1 to 2 RT dt. Okay, so I have one question, I guess. Oh, so I have a question about. Okay, so very good. No questions. Okay, so right. So well, let's do this first one, right? So what is the integral RT dt? So this is the solution then. So what is this integral? Well, we are supposed to integrate term by term, right? So this is equal to integral ln t dt I plus integral e to the negative 3t dt j plus integral tan t dt j. So I just continue here. So this is equal to, now, so term by term, what is the antiderivative of log t or ln t? You remember? Hmm?
Is it t ln t? Or
That's close.
ln t over
T
t?
ln
T
t.
over t?
No, you're close. Try again. Yes.
Is it t ln t minus t?
Yeah, this is the perfect answer. Of course, plus some constant. Right. So this is equal to t ln t minus t plus some constant. But this constant depends on this component. So we just put a different constant for each of them. So plus c1 and then I. Now, antiderivative of exponential of minus 3t minus 1 over 3 to the minus 3t. Negative 3t. Plus, again, I put c2 times j. And then plus, what is antiderivative of tan t? Yeah, tan is, what is it? Sine over cosine, right? So because tan is sine over cosine, so let me write it here so that make sure. So the issue is you want to know integral of tan t dt, that's integral sine t over cosine t dt. So this we notice is the derivative of this one almost, except that there is minus sign, right? So you can take this as your variable, for example, u. So let u, I mean, I'm just doing change of variables so that the steps become clear to you. Let u equal to cosine of t, then du is equal to negative sine t dt. So this whole part, top part, is negative du. So this is equal to what then? So integral, so this whole integral then is equal to integral. So what is it? I mean, we have minus sine t dt is du. So this is negative du over u. What is antiderivative of negative du over u?
Negative ln?
Negative ln
Ln u.
Ln u, yes, but ln absolute value of u. We should put absolute values on. That's very important. Right? Negative ln absolute value of u. And then, of course, plus some constant. So this constant, we call it C3. It doesn't matter. Because okay, now, but then you put back this cosine of t. So the answer is negative ln absolute value of cosine of t, right, plus C3. Okay, so the last component then is really plus negative ln absolute value cosine of t plus C3. So you can write this in a different form. You can just, well, I mean, that's good enough for me. There are three constants of constants, C1, C2, C3. So it's like a vector valued function plus an unknown, a kind of constant C. But the constant is C1, C2, C3. It's a vector itself. It makes sense. Now, the definite integral, you just use this result and evaluate between A and B, right? So that's, any question? You cannot read it?
Did we multiply the last term by k?
Pardon me?
Yeah, you're forgetting a k at the end. Did we have to multiply the last?
Oh, there's a k, absolutely. Thank you so much. Yeah, thanks. Yeah, exactly. Yes, there's a unit vector because the result is, otherwise it would be a very, very strange object. It's like it has two vector components and one scalar. They cannot be added. It's just not possible to add them, right? Well, you can create some new creations. I mean, just add these things as possible, but not in this course yet. Okay, so the definite integral again. So let me go back to the last part. So now we want to compute, what was it? Integral from 1 to 2, I suppose, right? It was RT dt. Well, we have to compute these things from 1 to 2. So this would be t ln t minus t from 1 to 2 I plus the next one, negative 1/3 of e to the negative 3 to 1 to 2 j plus the last one is negative ln absolute value of cosine of t 1 to 2 k. So, well, you can just subtract those values, put those values and subtract one. So that's not a problem. So you can finish it. That's okay. So that's good. So we covered the integration, which is an easy topic, but it's discussed in the book, so we should. Now I want to give you any questions about this? No? Any questions? No? Okay. Now, let us look at one of these examples of arc length parameterizations that we discussed, because it's good to practice them. So here is another example. Yeah, so the question was, find the arc length parameterization of this curve R of t equal to 2 cosine of 2t 2 sine of 2t and t. So t now, in this case, well, I mean, it could go from 0 to whatever number you like. Okay, yeah, from 0. Okay, so first of all, can you tell me what kind of curve is this? Yes, goes up. What is it?
The spiral.
Spiral, yeah. So that's a spiral. So what we're supposed to do? First of all, we are supposed to find the arc length as a function of t, right? So first, solution. First, find this function s of t, which is integral from 0 to t, normal r prime of. So I used tau last time, but you can use u or whatever. But tau, I like tau, so tau in distinction from t, right? So d tau. So this is the situation. So this is a spiral. So when the value of the parameter changes from 0 to t, you're traversing along this curve like that. So this is like, I mean, so this is like this whole length is s of t, and we are interested in computing that length. So what is that guy now? So this is equal to integral 0 to t. Well, this is normal. What is our prime of t? We have to differentiate this. This is -2 times 2 makes it 4, -4 sine of 2t. And then we have 4 cosine of 2t. And 1. Norm, t is bad, tau. But my t and tau are similar, so I'm kind of safe now. It's tau, right? Okay, so let's compute that. So that's equal to the integral 0 to t. Now this norm is the square root of, what is this guy? This is 16 sine squared of 2 tau plus 16 cosine squared of 2 tau plus 1 d tau. So this is equal to integral 0 to t. Now, so it's a lucky situation. It's designed to be like that, actually. Sine squared cos squared is 1, so this is 16 plus 1 d tau. 0 to t square root of 16 d tau. So what is the result? What's the result of this integral? Yeah. Root 17t plus?
C.
Okay. This is a definite integral, right? So they can't be any constant. It's just what you said, right? Exactly. Root 17t, exactly. That's it. Yeah. Just we make sure that we understand this is a definite integral. Okay. So this is s of t. Remember, we started from here and we end up here. Okay, so this is what we have got. S of t is equal to root 17 of t. Okay, so next step, this was the first step. Next step is to find the inverse function. Right? Next. So we have to find the t in terms of s. So t for s. We get t is equal to 1 over root 17 s. Again, it's a lucky situation that the relation between t and s is linear. I mean, there's just this factor, but otherwise, it's very similar. They're very, very similar to each other. So we found t as a function of s. Okay. So remember, this s is arc length. As a function of t. Now we are finding t as a function of arc length. We're finding the inverse function, right? And so what we're supposed to do, we are supposed to replace t here by s, and then we are done. Okay? So finally, replace t in r of t by s. So we get r as a function of s. Is it visible inside? Yeah, we get r as a function of s equal to 2 cosine of 2t, but t we found is, so it's 2s over root 17, 2 sine of 2s over root 17, comma, t is just 1 over root 17. This is the arc length parametrization. So we have written everything in terms of arc length. What's the difference between these two parameters, s and t? Just intuitively speaking. Oh, the side of the board got cut off. Oh, yes, sorry. Hopefully this is better now. Is it better? Very good. Very good. Yeah, I have a kind of unstable arrangement here, so it just, my laptop moves, kind of slides on the chair. You have to come and see here. It's quite elaborate system we have. Right? It's state-of-the-art camera and yeah, production, I would say. Okay, Western, listen to me. Give me a cameraman. Okay, so yeah, I can read. Right. So now, yeah. So the question was, can you tell me the difference between t and s? We have two parameters. We can parameterize the curve in terms of whatever we like, but what's the difference between t and s in this case? You see, the parameter t is like a dummy parameter. I mean, it's like a parameter that it just came by random, it seems. Has no geometric meaning, this parameter t. On the other hand, the parameter s is kind of, is very, very important. It has geometric meaning. It measures arc length. So if you compute, for example, r in this parameterization, if you compute r at 1, you mean where the location of this curve at point s equal to 1 is, and then you know that exactly the arc length from 0 to that point is exactly going to be 1. So S really measures the arc length. It's a very, very kind of canonical, I don't want to use religious terms, but it's a God-given parameterization. Okay, so yeah. Anyhow, so we have that sort of canonical or very basic geometric parameterization. And the importance of this parameterization will come right now. You'll see how important it is. But let me just notice one. Any questions about this? T is time, S is distance. Yeah, I think that's nice. That's a nice way to say that. Yeah, I like that. T is time, S is distance. Yeah, that's a good way. I said T is dummy variable, but you can imagine it's time. Yeah, S is distance. Yeah, yeah. I like this answer actually. Yeah, very good. Now let me so give you kind of another take on this arc length parameterization. So derive a formula that's so important, we can use it. Okay, so so since S of t is equal to integral from a to t norm of r prime of tau d tau, right? From here we get that ds dt, right? We did it last time, I remember, but let me write it again. ds dt is equal to norm of r prime of t. So this is an important formula, right? So it just shows that the rate of change of distance is exactly measured by speed, right? So, i.e., rate of change distance is measured by speed. By the way, that's what we expect of speed, right? The speed measures the rate of change of distance. That's kind of intuitive notion of speed that you've been introduced in high school or elementary school, whatever, right? So that makes sense. So, but this is a kind of three-dimensional version of this, right? This is important. Rate of change of distance is measured by speed, and this is the formula. So this is. Okay. So now we are going to use this idea of arc length parameterization, distance, and also. So let me recall. Also recall. You recall what was the unit tangent vector, right? Tangent vector. So what was it? The notation was t of t, right? It was r prime of t divided by its magnitude. So this is the curve moving, and along this we just chose so it's a vector field that moves along the curve. It's always tangent to the curve, and its magnitude is always 1. We made it to be like that. And we can always do that provided this r prime of t is non-zero. So you're allowed to do this, you're allowed to divide as long as r prime of t is non-zero, and that's what we are assuming about these curves. Otherwise, you can define this sort of vector field along this curve that's always tangent but has a speed as a length 1. That's why it's called unit tangent vector. Okay. Now, I want to use the fact that so norm of t of t is equal to 1 for all t. That's the magnitude. Now, I want to use this to derive a kind of nice relation between t and the derivative of t. So I say this implies that t prime of t dot t of t is equal to 0 for all t. So this is a very important relation that I need later on, so I'm going to derive it now. So in other words, the situation is even more general. I'm saying if you have a vector valued function whose length is 1, then the derivative of function is always orthogonal to that vector, to the position vector. Its velocity is always orthogonal to the vector itself. Can you tell me why? So what is the situation? I have a vector that moves in space. Well, okay, so this is nice actually. Maybe I should go here. So so this is imagine this is unit length, right? So this vector is moving in space. So okay, so here is fixed, and I'm just moving it in any which way you like. Any which way you like, it doesn't matter. As long as its length is constant, the velocity that's measured by motion of the tip of the vector is always orthogonal to the vector. Why is that? That's an interesting thing about motion of bars in space. Yes?
I guess because the tip, like it can only move left and right. You can't, as long as the length stays constant, it can't move up and down.
Yeah.
So it can only move in the orthogonal plane.
Right. Intuitively, that's right. That's the right intuition. And we can drive it mathematically as I'll do now. In fact, that's the right intuition. Right. So proof. What does this relation means? Norm of t is equal to 1. It just means that t of t, right? T of t dot t of t is equal to 1, right? So this is norm of t squared equal to 1, right? So I have norm of t squared is 1, capital T squared is 1. This follows from this. I mean, if norm is 1, square of norm is also 1, and vice versa, because norm is not negative. Right? So we have that. So this is squared is equal to 1, right? So then this implies, in fact, this is if and only. So the fact that norm is 1 is equivalent to the fact that t dot t, capital T dot capital T is always 1. And now what we can do? We can differentiate this function. So here, so I'm going to write it here. So you just write tt dot tt. So let's say ddt of this. This is equal to 0. Look, you have a function. This is really an honest, normal, usual function, one variable function, right? Because it's a scalar. So you have a function whose value is 1. So if you differentiate it, its derivative is going to be 0. So that's the right hand side. Now, what about the left hand side? How do you calculate derivative of t dot t? That's where the Leibniz rules for derivatives come into use, right? So what we can say, so I continue here, over. So you get t prime of t dot t plus, so let me put tt plus t dot t prime t equal to 0. This is Leibniz rule, as this, or product rule for vector or for dot product, right? This is Leibniz rule. Okay, so then what can we do? Look, this is t prime dot t, this is t dot t prime. But we know that the dot product is symmetric, right? So we can just write it twice, t prime t dot t in 0. So in other words, t prime t dot tt is equal to 0. So that's what we wanted to prove, right? That's what. So if you move in such a way that you're always on the surface of like a sphere of radius 1 or whatever, then your velocity is always going to be orthogonal to. Would this work for all the tangent vector norms which equal to a constant, not just one? Yes, exactly. That's a wonderful question. Thanks for asking this question. There is nothing special about 1. You see, I mean, you can take a bar or vector field of any length. As long as the length is constant, 2, 3, root 5, whatever, then the answer is, the same argument goes through, right? Because here we just use derivative of 1 is 0, you can say derivative of 5 is also 0. Yeah, absolutely. I like this, by the way. It gives you some sort of authority, right? No. Scary. Okay. Okay, so yeah. Okay, so now we have everything we needed in order to talk about the kind of highlight of this chapter, I would say, which is curvature. Any questions about this? No? Okay, so this is the high point. Chapter 3, I suppose this is chapter. This is chapter 3, right?
Yeah.
I guess it's chapter 3. That is curvature. Maybe you have been introduced to the idea of curvature in Calculus 1000. That's possible, and maybe not, but it doesn't matter. So I'm going to discuss it from start. So what is curvature? So this is supposed to give us a measure of how much bending or curving a curve has, right? So this kind of measures, curvature measures bending or curving of a curve. I mean, this is a very vague, intuitive, general concept, but anyone can say this. It doesn't matter. First of all, we have to understand the question more precisely. What is the question? So we want to have a measure of bending such that, for example, straight lines, this gives us curvature is equal to 0 everywhere. We want to have this measure. And we want to have a measure such that for circles, radius bigger and bigger, so I want this to have higher curvature, to have more, I want this to have more bending, more curving compared to this, and this less, and this one is even less, right? So, so this I would say here, K here, bigger than K here, bigger than K here, K here, bigger than. So as you move on, your curvature, I want to go down. And you can see that there should be some dependence on the radius, right? It should be some dependence on the radius. But the question is exactly how this would depend on the radius. So you sense that this K should depend on radius, but how? And you feel that it should be kind of inversely proportional to the radius, right? Because we say that the radius bigger, the curvature is smaller, right? But how? It could be 1 over R2, it could be 1 over R, it could be 1 over log R, or some strange function. Who knows what? So that's where so these are really questions that mathematicians who thought about the idea of curvature had to struggle with. I mean, how you can make sense of this concept? How can you quantify this idea, this vague general idea has to be quantified so that at the end we come up with a number that can be calculated and it's kind of useful and reflects something about reality. It's not just some abstract concept. So the answer is this. And then it takes some time to understand the answer. So this is the definition. The curvature of a curve R of t defined as kappa at some point t. So the curvature of the curve R of t, so at the point t, so I would say maybe at time t. But really time is not of any essence here. It's just at the moment, at the point, really, that's represented by this parameter t. The value of the parameter t, time t is defined as kappa of t is equal to norm of, I would say, dt ds. So this is the golden definition. So let's see what it says, i.e. So you can see it here, i.e. curvature is equal to rate of change is equal to magnitude of rate of change of this unit normal, unit tangent vector with respect to arc length, which is S. So let me put it S here, because I used this. With respect to arc length. With respect, so I'll continue over there, with respect to the arc length. With respect to the arc length. So in other words, this mysterious definition, it's quite a definition. One has to think a lot about this to kind of grasp some aspects what really this means. So here is the curve, and we are defining this unit tangent vectors. That's fine. Understanding unit tangent vector is fine. But here it's not t in terms of parameter time, right? It's parameterized in terms of s. So we have changed the parameterization. And we want to measure the rate of change with respect to s, not with respect to time. So we want to measure how fast the tangent is changing, the tangent vector is changing. We want to measure the speed of change of the tangent vector with respect to arc length, not with respect to time. And so this is the ingenious aspect of this definition. We are not, if you just wanted to use t, anyone could have given this definition. Let's take dt dt with respect to time. That would be very easy. But that's not that. Somehow it's identified that the arc length is the important thing. So that's the importance of this definition. And that's the difficulty of understanding this definition. So now the formula, so now this definition is very good, but it's totally useless. Sorry, that's, so maybe I have a comment here. Would this work for all the tangent vector norms which equal to a constant, not just one? Oh yeah, this was an old question. It's not a new question. So let me make a comment. Star is good conceptually, but useless to calculationally or computationally, so useless computationally. Yeah, there are always these two aspects of things, right? Something you understand conceptually, but you cannot compute with the original definition. Sometimes formulas are easy to use, but they're totally mysterious. You don't know why these formulas are. So the formula that I'm going to derive to replace this is totally mysterious, but totally useful. That's the opposite. So you see this dichotomy between the two things, usefulness, computational usefulness or computational applicability, and conceptual aspects. So you should keep these two things in balance. So instead, we shall use the theorem. So this is a theorem that I'm going to prove now, and it will convince you how to really effectively compute without going through this very, very difficult kind of calculus. This would be very difficult because parameterizing your unit tangent vector in terms of S is a difficult task. Well, I mean, we can compute arc length only in very, very special cases, right? So the theorem is this then. So let me put it here. First of all, one is that K of T is equal to, there is a very nice formula for this, which would be norm of T prime of T divided by length of R prime of T. Yes, very good. See, this one is already an improvement, right? We are writing everything in terms of T, not that complicated variable S. Now this is already some improvement. This is good. And the second part is it should be a total surprise to you, and it is surprising. So part two is that kappa of K of T is actually given by norm of R prime of T cross R double prime of T divided by norm of R prime of T cubed. So you see, if I gave you to start with this definition as curvature, you should feel completely offended, right? I mean, why this definition? I mean, this doesn't make sense. I mean, why this definition is reasonable? You should have. I mean, you would have complained to me that this guy just this is teaching like a cookbook. You know, do this, do that, and you'll get your dish at the end. That's not what we do. We start from some definition, kind of made sense, and now we're going here. So this is the second part. And third part is if y is equal to f of x, x say between a and b, then the curvature of the graph of this so this is the curve of graph, right? So AB. So the curvature of the graph is given by K at x is equal to, I believe, the second derivative of y. Well, y is equal to f of x divided by 1 plus y prime of x squared to the power 3 over 2. Okay. So we have these three definitions. These three kind of results. And this is, of course, only in 2 dimensions, right? So this works only for 2-dimensional curves, which are graphs of some curves, right? So this is only in 2 dimensions. It's not the most general two-dimensional case either. It's those curves that are graphs. I mean, we know that not all curves are graphs. It's a special case. This is in 2D. This is very general. And this is the most useful. And this is our initial point. So the way I'm going to prove this theorem is I'll prove this first. I almost proved it actually. I did prove it last time. And then this one, and then that. So I think we are done now. This remains to be done on Wednesday. Any questions or comments? What's the last equation again? Oh, what is the last equation? Oh, this one? K of x equal to absolute value, sorry. Absolute value of y double prime of x over 1 plus y prime of x squared to the power 3 over 2. Oh, yes, no, that's correct. No, everything is okay. What's the last equation? Yeah, I answered.
So you said not all graphs are curves.
Speak louder, please. Speak louder.
Okay, sorry. You said not all graphs are curves, or vice versa. I'm not sure. Can you show why? I don't really understand why that's the case.
Oh, not yeah. For example, imagine you have so graphs are obtained by a function like this, right? So now imagine you have a curve like this. In 2D, you have a curve which is like this. Oh, this is a curve, right? I can write this as in parametric form, like f of t over g of t. But you cannot write it as y equal to f of x. But this is okay. So the message is this. There are more possibilities in parametric forms, f of t, gt, than x and f of x. You see, this is also a parametrization, right? Because the graph is just a parametric version also, right? But here the function, so let me put it like g of x or something. This function is just very simple function, x. What if someone chooses here like sine x and then cosine x, for example? You cannot write this as a graph. Got it?
Yeah, that sounds good. Thank you.
Very good. Any other questions or comments? Okay, guys, thank you. So I just stopped the thing, but not the video. So let me just stop recording.